Section 3.2, logarithmic functions and their graphs. So now we're going to look at the logarithmic function, the inverse to the exponential. We're going to look at how we can write those, how we can solve them, and also some properties of their graphs. So every function of this form, an exponential function, passes the vertical line test and the horizontal line test, which means it's one-to-one and it has an inverse function. This inverse is called the logarithmic function. And I knew how to spell it this time. Didn't hesitate one bit. So the definition of a logarithmic function, because it's an inverse, we have y equals a to the x. It had to switch around. X and y have to change. So x equals a to the y. That's how you create the inverse. And then what we do is we introduce a logarithm notation. Okay, and the logarithm is how you write the inverse. So the x equals a to the y. What we do is we take log base a of both sides. So the log base a of this side becomes log base a of x, which we see right here. And then over here, the log base a eliminates that a value. It's the inverse. Inverses are supposed to eliminate. A logarithm eliminates an exponential. So the log base a eliminates the a, leaving you with just the y. To write out what I just said, so we take log base a of both sides. So we have x equals, so log base a of x, we have log base a of x, log base a of a, the log is the inverse of the exponential, so it cancels all that out, leaving you with just the y value. So that's how the logarithmic function gets created. Now what I like to do is I like to remember that a logarithm has all the evidence from the original exponential. So when I go to evaluate logarithms, what I really do is I think, okay, what exponential function was the source for this inverse, this logarithmic function? So I kind of have some ways that I think about these, okay? First, I think about this right here. Now the f of x, I'm going to call that the exponent. The log base 2, the 2 does remain the base, and the 32, I'm going to call that the answer. So what I'm doing is I'm taking the logarithm and I'm identifying all of the pieces and where they would have existed in the original exponential. Because we already know how to solve exponential functions. Why not just use that knowledge to help us with these logarithmic functions? So it's like a crossover. The base, go across the equal sign, the base to the exponent gives me the answer. So 2 to what power, crossover, equals my answer, 32. And from there it's pretty straightforward. What number, 2 raised to what power, gives you 32? Well, of course, that would be 5, and that's your answer. Over here, okay, again, the f of x is my exponent, so I'll put, just remember that's my exponent, my base 4 is my base, my 2 is my answer. So 4, base 4, cross over to what power equals 2. Now what you have to remember is that when you're dealing with exponentials, it is possible to get an answer smaller than what you started with. That means that your exponent is going to be less than 1. It's going to be some fraction or decimal. So you have to think to yourself, okay, 4 raised to what power would give me 2? Well, the way to work with that is with square roots. Okay? Square roots make a number smaller. Square roots can also be written as exponentials. For example, the square root of x is the same as x to the 1/2. the cube root of x is x to the 1/3. Okay? So square root of 4 would give you 2. That means the exponent it's being raised to is 1/2. So again, I like to just work with these and kind of take them and rewrite them as an exponential function, which I'm already pretty comfortable with solving. Over here, this is my exponent, my base, and my answer. So my base, 3, cross over to my exponent equals my answer, 1. So 3 to some power gives me 1. And of course, you know, anything raised to the 0 power gives you 1. Here, my base, 10, raised to some power, cross over, equals 1 over 100. Now 100, let's try and use that one-to-one property. 100 I can rewrite as 10 squared. So 10 to a question mark equals 1 over 10 squared. Now when you're working with exponents, when a number moves from the numerator to the denominator, that means a negative exponent was applied to it. So if it's a positive 2 down here, we have a whole value 10 here, we can take this 10 to the 2, we can move it up into the numerator. But what that's going to do is that's going to make that exponent a negative. And now our one-to-one property, our answer is -2. So take a moment to look at the other 4. Check your answers with my completed notes online. See how you do with them. So I find a lot of times these just take practice. All right, kind of the more you look at them, the more you kind of remember the process, what you do. All right, the base, cross over to the property. So these are in your textbook as well. You can take a look and fill this in. Again, think about section 1.6, your library of parent functions, kind of what are some of the properties of these logarithmic graphs. The natural logarithmic function. So let's say you have base e. Okay, this is a little blurry, so let me write it out for you. F of x equals log base e of x. What we do is we don't write the log base e. Instead, we do ln, the natural logarithm. It's kind of like log base 10 of x. Whenever we have base 10, we don't write the base 10. We just call it log of x. Just a little bit of shorthand there, okay? So just recognizing that ln means you have a base of e, and on the next page of your notes, there are some properties that you can fill in from the textbook or my completed notes as well. Some properties that can help you in solving some exponential and logarithmic equations.